If you step into a market with exactly 15,000 shillings in your pocket, you can buy ingredients up to that exact amount, but you cannot spend a single shilling more. The physical world has strict capacities too. By law, a standard taxi operating in a park like this has a strict maximum of 14 passengers. It can carry fewer people, but it is illegal to carry 15. Mathematics uses inequalities to translate these everyday physical constraints and financial budgets into exact calculable boundaries. This diagram maps out the 4 mathematical symbols we use to define those boundaries. The crocodile's mouth always opens toward the larger value. We have strictly less than, strictly greater than, and the inclusive versions, less than or equal to, and greater than or equal to. When we map these onto a one-dimensional number line, the inclusion of that specific limit matters. An open circle, like the one here on 0, means the number is a boundary but isn't allowed itself. A closed, solid circle, like the one on 2, means the number is safely included. That visual difference between an open and closed circle tells you instantly if a specific limit is legally allowed or strictly prohibited. Solving a linear inequality follows the exact same sequence of adding, subtracting, multiplying, and dividing as a standard algebraic equation, with one critical exception. This animated proof shows why multiplying or dividing by a negative number breaks the logic if we aren't careful. We know 4 is greater than 2, but if we multiply both sides by -1, we get -4 and -2. -4 is actually smaller. To maintain mathematical truth, the sign must flip. Watch what happens when we solve -2x is greater than or equal to 8. When we isolate x by dividing both sides by -2, the symbol visibly rotates to less than or equal to, giving us x is less than or equal to -4. Forgetting this negative flip rule is the most common error in early algebra. Applying it is the only way to find a true mathematical boundary. This graph shows a standard Cartesian plane, where we translate those boundaries into a 2-dimensional space. To start, we pretend the inequality is an equal sign and draw a straight boundary line, like y equals x plus 2. Just like open and closed circles on a number line, the type of boundary line matters. The boundary shifts to a solid line for inclusive limits and a dashed line for strict non-inclusive limits. A boundary line splits the graph into 2 halves, so we pick a test point to determine which side satisfies our rule. Using the origin at 0, 0, we substitute 0 for x and 0 for y. 0 is less than or equal to 2, which is a true statement. In standard practice, we shade out the false, unwanted region. By crossing out the mathematical rubbish above the line, the true, safe region below remains clean and visible for making decisions. This challenge prompt on screen asks you to solve 5 minus 2x is less than 13. Pause the video, find the algebraic answer, and decide if the boundary line would be solid or dashed. Let's walk through the solution. Subtracting 5 gives -2x is less than 8. When we divide both sides by -2, that crucial rule kicks in. The less than sign flips to a greater than sign, leaving x is greater than -4. Because the symbol is strictly greater than, the boundary is a dashed line. Mastering this combination of the algebraic flip and proper line identification allows us to solve complex real-world systems. Out in the real world, boundaries overlap. A farmer protecting a grazing pen on a terraced hillside has to map out a safe region defined by multiple intersecting rules at the same time. This coordinate grid translates those physical fences into mathematical boundaries. We start with the limits x is greater than or equal to 0 and y is greater than or equal to 0, drawing solid lines along the axes and shading out the negative areas. Next, we add the diagonal limit, x plus y is less than or equal to 4. Testing the origin shows the safe region is below the line, so we shade out the upper area. What remains is a perfectly clean, unshaded triangle near the origin, marked R for region. The corners, or vertices, meet exactly at 0, 0, 4, 0, and 0, 4. Bounding an area with multiple inequalities is the exact tool used by engineers and planners to optimize constrained resources and map out safe zones in complex environments. This comparison table maps out the visual rules we've covered. Strictly greater or less than symbols always pair with open circles and dashed lines, while inclusive limits pair directly with closed circles and solid lines. To ensure your boundaries are always accurate, rely on the two absolute laws of inequalities. Always flip the sign when dividing or multiplying by a negative number, and always shade out the mathematical rubbish to leave a clear path forward.